Good morning, students. Uh, I only see 22 students joining in. Are people aware of the class? Ishita,
Yes, ma'am.
are students aware of the class?
Yes, ma'am.
Or what happened? Why there is nobody? Almost just 25, 27 students.
Maybe we are having actually so many quizzes
Uh,
today and tomorrow, so maybe because of
okay,
that.
you have plenty of quizzes today and tomorrow?
Yes, quizzes and other submissions also.
Okay, okay. I think let me do. Uh, I'll try to wind up today, but I wanted to do few more things which I couldn't do because of the two holidays which came up on Friday and Monday. So I had to cut short. And moreover, Wednesday I couldn't engage the class. So I will try to do whatever I can. And if I am a bit short, so kindly give me one slot somewhere in the next week so that we can wind up. Okay. So I have brought in PPTs so that we spend less time on drawing the circuits and quickly review what I was talking about, the various TTL based logic families, the way it started, and then do some of the important things. I definitely need one more session with you to do at least some good interfacing. These are some of the packages which are available today when you talk of a IC. Now there is a classification based on even the package type. Okay, the most popular packages which are used in practice is DIP, because you would recall in your even electronics engineering lab in first year, you would have used a DIP package, which means a dual N line. You have pins coming out on the two sides of the IC. Okay, but now the surface mount devices are more popular, and people use quad flat package or thin quad flat pack, and these are the standard ICs which are now available for most circuits. Though this 7.4 and 5.4 series of TTL and even CMOS 4000 series continue to come in DIP for educational purposes. But for all other professional systems and research oriented development, people use quad, flat pack, or other type of packages. There people also use a grid package and all that. We are not going into the details of it, just a mention so that you know there these are the words available, or these are the variety of packages which are available. Now, when you come to the various technologies, uh, see, this is the first one which you did in even electronics engineering, a diode logic. Okay, so you will recall this circuit which you did. So in this circuit, if you recall, this was done in your electronics engineering where you made a AND gate. So the two inputs were on these 2 points, and this is the output node. And you would recall only when both of them are high, this diode is in cutoff because your this node is at higher potential, and this is a high resistance. So most of the voltage drops. The resistance of this device, if it conducts, will be very less. Okay, and since a lot of potential has fallen over here, this potential is definitely less than the high 5 volt which you are applying over here. Okay, so this is this does not turn on, because to turn on this node should be at least one diode drop less than this node, which is not there. So both the devices turn off, and only in that condition this node is at 5, and this makes this diode turn on, because this is a low resistance path, and since this is on, this node rises to a high voltage. High voltage means within that logic range. Okay, so this node was rising up to only one diode drop, 5 volt minus one diode drop. So this will go up to 4.3 or something like that. Okay, depending on what diode we are using. If diode drop is 0.7, it will reach 4.3. Any one of them is low, logic low, then this device, the corresponding device will turn on, and this voltage will set up or get sync through that node. Okay, and this device will not, because this is only one drop higher, it will remain zero point 0.7, and this zero point 0.7 will not be enough to make this go high. Okay, because this is the low resistance path, it will drain from this. This is a higher resistance path, so everything gets sync and this becomes a low node. Okay, zero point 0.7. Okay, and therefore this node will not reach a high voltage, it will reach a low voltage. And low voltage um, depends what value it will come, but not higher than one diode drop. Okay, so this was the one circuit which you had done, but it can only make your NAND gates. Okay, this was a limitation, you can't have even inverting gates out of it. Then came a resistor transistor logic, where you used a transistor as a switch. Now there are two switches, for example here, this is a NAND switch which we have shown. There is one resistance which is just 10 kilo ohm, and here it is one resistance which is 4.7 kilo ohm. These are fixed values if I am using this transistor. So one has to work out what resistance value you need to put it here. I am right now not going into all those IV equations and details of calculating these values. Okay, but one can find out and do it, because I don't think that is the motive right now. This is only a review class. So you will see if this is high, okay, and also this is high. If this is high, this VBE will be one diode up. Okay, this is a junction. So this turns on. This turns on means this can conduct, because this is also a high volt over here. This can conduct. Similarly, this can conduct. So there is a current flow in this direction, and this transistors can sync this node, and this node comes to low value. Now what low value it will come is 1 VCE for this and 1 VCE for this. Typically for a silicon diode, your VC is 0.2 volts. So when this device is conducting, this is the VCE is zero point 0.2 volt. Here also it will be 0.2 volt. So you will get a 0.4 volt over here. Okay. And as soon as any one of these two value is high, if they, low, one of them is low, that corresponding transistor will have VBE less than the diode potential. So it cannot turn on. The transistor will not turn on, it will switch off. And if the transistor switch off, it is like a open switch, and therefore this node cannot sync. So this node will reach a high voltage. So whatever is here, the same voltage should reach over here. because there will not be any potential drop and in that condition. Okay, so but what is the severe disadvantage with this circuit is, if you recall, when these two are on, there is a continuous current, DC current flowing, and it is a high amount of current. So power drain is one of the major problems in this circuit. Okay, and nobody uses RTL at this point in time. Okay, it has gone long back, but only to understand the logical uh, how evaluation occurred, I did tell you. Then came a DTL. Okay, and DTL you will see is something similar to what we had, a diode AND gate, which we had built. This much we had already built. There is a additional diode only coming up, nothing different. It is the same logic for AND diode logic. And after that, we are putting a inverter, which we did in RTL. Okay, so it is based on the two technologies which we did earlier. And this transistor is basically doing an amplification. So here, even if you have a voltage drop, okay, of two diodes, now this is inverting and providing a full VCC. Okay, so this is only a inverting switch and used as an amplifier. So this has some less power consumption, because this can work on lesser current, but not significant power drop will be there. And this is slightly faster than RTL, because in RTL logic, the NAND gate had two transistors in series, so it becomes a slightly slow. Here it can be faster, a bit faster. Okay, this was 10K calculated earlier. Now it is 4K. So the power also is less. Power is directly proportional to what you are putting a resistance, and you can calculate VI, and I is directly proportional to your resistance which you are using. Okay, V by R. So V square by R becomes your power. Okay, so as soon as you kind of change this, it changes your power as well. But even this technology is no longer used. Nobody uses it. It's if you want to go into the details of these two, three, for your curiosity, you can read the book by Manu. Manu has these technologies. No other book I could find these are available, or you can find them on internet. Now, most TTL circuits, which is the most popular among BJT technologies, is AND and NAND gates, which use multiple emitter transistors or multiple diode junction inputs. We will show in a minute for a review. NOR and OR gates use separate input transistors. So the configuration is slightly different. The input is kind of a cathode of a PN junction, and high input will turn off the junction, and if you put a low input, it turns on the junction. We will see a structure and you will get it clear. And the most popular configuration used in TTL circuits is totem pole output configuration. That means one transistor sits over the other transistor. That is what is the totem pole literal meaning. But you have two more configurations. One is open collector, where you remove the pull-up transistor from the structure and you put a load. For example, if you want to drive a uh, your LED or a lamp through a TTL transistor, okay, then you cannot use totem pole. You need a open collector configuration. So I'll show you and tell you in a briefly. Now this is that circuit which you should have done in first year. This is a AND gate. So you can see this is a multiple emitter transistor which is used. So each emitter is connected to a input. Okay. So the if you have two input NAND gate, you have two emitters. If it is a three input, you need a three emitter transistor. And if you see what is the equivalent circuit over here, is this. This resistance is the same, this resistance. This Q2 is the Q2. Only this transistor, if we expand, is something equivalent to our diode logic, which we had done earlier. Okay, so you have every input being connected to the negative end or N end of the diode, and P ends connected together to a back to back diode, and then it gives the output to the Q2. Now this is kind of amplifying stage which passes this signal over there, and this is the totem pole configuration. Okay, so if this both the inputs are high, only then output goes low. So if both of them are high, this turns off, this turns on. You can kindly read the detail. This is very well explained in Toki. Okay, and once you read it yourself, the details, all the 3 4 pages, you will be very clear about these TTL technologies. So high, you know for sure it comes through this when this is off, and if this turns on over here. Okay, and let me recall, the low goes through this node becomes high, and this high becomes whenever this is on. If this is off, this turns on. If this is on, this turns on. Okay, and if you are using it in an application, for example, what I said is you are driving a output which may be a lamp or a LED, then that load is connected to this output node directly. So you need to have a configuration where this is not there. So this portion is eliminated. And if you eliminate these three devices, it becomes a open collector configuration. This collector of Q4 is open, not connected anywhere. And this directly can be connected to the load which you want to connect. Okay, so in those applications, you need a open collector kind of a configuration. And by looking at the IC data sheet, you can make out whether it is an open collector or a totem pole, or the third configuration could be a tri-state. If, for example, several gate outputs are to be connected or shorted, there are applications where you require them to be connected. Okay, so you cannot use totem pole, you cannot use open collector, then you need to use a tri-state configuration. So by looking at the data sheet of an IC, you know whether it is totem pole or open collector or tri-state, and you make choice of an IC accordingly, where I am using, so what kind of configuration is required. And this is very important when you are doing interfacing. Okay, you are building a circuit using these ICs, you cannot connect anything anywhere. You need to know which kind of configuration can be connected where. Okay, so these totem pole, typically if it goes as an input to some other IC, then yes, totem pole. Okay, if these outputs are being shorted together, several of them, then you need a tri-state. Okay, and if you have a load which is to be connected directly to the output, then it will be open collector. Okay, so this is a bit of working how it works. You can see when these are high, both the inputs are high, then this turns on means this node is high, this also turns this on. Now if this has turned on, the voltage drops here to zero point 0.8 volt. Okay, and this zero point 0.8 volt, because now this is on, this turns off because this is going low, zero point 0.2 volt. Okay, and this is another diode sitting over here, so you need zero point 0.2 and here one diode drop, so something like zero point 0.9, and this is zero point 0.8, so this cannot turn on. Okay, so if this cannot turn on, so this is open path, this conducts and it reaches the ground. So VOL reached is the VCE of this transistor. So it says less than zero point 0.4 volt, but it will be 0.2. For a typical BJT transistor, VCE in conducting mode is zero point 0.2 typically. Okay, so you will 0.4 because this is the standard spec given in the data sheet, that VOL does not rise beyond 0.4 volt. Okay, because if you have two transistors as I shown in the previous, then you are likely to reach zero point 0.4. Okay, this will be around 0.2. This I have already said to you that it acts as a current sink when your output goes too low, and it becomes a current source when your output goes too high. Okay, so I'm not going. This is how it works with a high. I can share this PPT file as well with you. You can have a look at it. But I suggest this has been taken from Toki itself, and therefore you can see the reference in the footnote. This is the book I am using. So please go through this book. There is no better book for this chapter. And I'm sure a soft copy of this book was circulated among the students, so everyone should have an access. If still anybody doesn't have an access to the book, please let me know. Send me a message, personal message. I can send you a personal PDF. This I have already said to you, this acts like a current source. Now this NOR configuration, if you try to make, this is a bit more complex because both the inputs have to be on different transistor because they are to be set parallelly. Okay, so this is, you find it less into the box, but you can go through it. There is not much difference, but the thing is the two have to be built parallelly. This totem pole configuration you can see is still the same. Okay, so you can just understand or try to go through the circuit, which is for TTL NOR gate. You must know TTL NOR gate configuration and NAND gate configuration. This is the TTL family evolution. It is started with 7.4 series because nomenclature is also important when you pick up your ICs. Then came 7.4S, which is Schottky series, and Schottky series was a bit faster because Schottky device as such has a deep saturation, and therefore it transfers the signal at a higher rate. So, but even this is absolute obsolete at this point in time. Then came was uh, low power, but it had this LS means a low power. L stands for low and S stands for Schottky, low power Schottky. But because power and speed are always goes opposite, so if you try to reduce power, the speed also reduces. Okay, and if you want to increase the speed, then you need to compromise on power. You have to give power. So there is one series available, which is a high speed HS series also available. But rather than HS, LS was more used. But even this is not used now, though we still have these series devices in our lab, but we don't purchase new devices. They are not available. Then there came 7.4. This was advanced short K. A stands for advanced. This was relatively quite popular series, and this was fast as well as some low power. So they had improved upon the technology. And this was another series. So AS and ALS are the more popular series. This had even low power. Okay. And this is another series. We have not bought ICs in this series, but this is also available. I don't recall what was the 74F parameters, but it was a change in the fabrication process, and why that is why it was cheaply available and it became a bit popular. And some I think it was more complex as well, putting in more devices on the chip. So the first kind of TTL ICs were 7.4 and 5.4 series, which was from Texas. And there are various manufacturers. So at times you will see before even 7.4 or 5.4, 5.4 you will never use because it is a military spec devices and they are very costly. So we just don't use them because, and 7.4 is a commercial series. So you will see SN written or DM or S written before 7.4. So this is the manufacturer who has produced it. SN is uh, the numeric, the alpha numeric code used by Texas. DM is for National Semiconductor. S is used for Signetics. These are the three prime manufacturers in this series. So you will see devices like DM7402. So what does it mean? It has been manufactured by National Semiconductor. 74 is means TTL commercial series, and 02 is the number. Okay, so 02 is a NOR gate. And similarly, this SN means Texas, and this is from Signetics. You will see all other fours are the same and they perform the same function. And I believe they even have the pin compatibility. So one can refer to the data sheets which contain the electrical characteristics, switching characteristics, and recommended operating conditions. They also specify whether what power variation can be kind of uh, how much power variation can be tolerated by a particular series. Okay. This is a kind of data sheet which you will see. So it will specify a typical VCC. So this is the nominal value which you will connect, but it has a 10% variation. So minimum can be 4.5 and maximum it can tolerate is 5.5. Okay, and you can see VIH. Now this is the data sheet for 74 ALS. So you can see this is a commercial TTL series of type advanced low power Schottky, and 00 is NAND gate, 2-input NAND gate. And this IC has 4 NAND gates on the chip or on the one IC or one package. Okay, so you can see the VIH input high, which is acceptable as high, is minimum, which is 2 volt. So 2 volt and above up to 5 volt will be taken as logic high. You see VIL is written as two values over here, 0.8 and 0.7. If you see the note over here, what temperature range you are working on, this changes the input low level. So if you are working between -55 to 70 degrees centigrade, then you have zero point 0.8 as the, which can be your maximum value of logic low. But if you go to a higher temperature, then this value reduces. It cannot take even zero point 0.8 as a logic low. So noise margin will cut down at high temperature. So you need to specially take care of this for industrial applications. If you are doing a chip in an industry where your temperature can rise beyond 70 degrees centigrade, then we have to design our circuit taking into 0.7 as consideration. If you see the currents, these are output high current and output low currents. So this minus only means the reverse direction. Okay, high is sourcing and this is sinking. So this is only relative to the current, the direction of the flow of current. If the current flows inward, then it is positive. If current flows outwards on the output node, it is negative. Okay, so and you can see the operating temperature range given here for this IC is -55 to 125. Okay, whereas see the other IC, this is military 7.4 and this is sorry, this is 5.4 and this is 7.4. So this is for military, so it has more tolerance, tolerances, and it is more specified for a temperature range. It can work for a wider temperature range and the values are also calculated accordingly. But if you see here, it only works from 0 to 70 degree commercial IC. Okay, so I cannot work or make a circuit using this 7.4 series IC for a temperature range below 0 and above 70. Okay, so I cannot do it, and therefore you see only one value of VIL. Somehow there could be a question why there are two values for VIL but not for VIH. It just comes from the measurement technology house. You do a measurement on several thousands of devices and then you draw from the statistics. Okay, so and then the switching characteristics, what you are interested in, the propagation delays. Okay, the tau p LH when it is going from low to high and high to low, the output changing from high to low. Okay, so you can see the values over here. Now this is your 5.4 series, this is your 7.4 series. Okay, all other conditions taken are the same. So you can see the maximum time taken over here could be 15, it could be, it is 11 over here. And temperature conditions are already given because here temperature variation is wide. So on some temperature, it might take a larger time to propagate. That is why it is higher. And you will see even for propagating or changing the signal from high to low, it takes slightly large time. It may take, though the best timings are the same, but these variations are more because your operating conditions are more. So if you deviate from 0 to 70, then it might take more time. This is what it conveys. So we need to read the data sheet when we are using an IC for a particular application. We need to identify what parameters I need for my particular application, and accordingly I'll choose a IC. Okay, you can see some of the other values of the same ICs. Okay, I think I'll take them up when we do interfacing. So you can see these are the typical characteristics. These are the typical characteristics for the various families, 7.4 series, 7.4S, 7.4LS, up to 7.4F. So you will see the propagation delay. 7.4 typically, the 9 nanosecond. For Schottky, it came down to 3 nanosecond. But when you take a low power series, you have to compromise on speed. It increases the delay 9.5. But then you come to advanced Schottky, which is having high speed. You see this, and you can even compare with power. Keep checking the power. The power has increased as soon as you reduce the speed. Here you increase the propagation delay, but it is a low power, so power is being focused. It is still better if you see the product. That is the actually figure of merit. So it becomes 90 over here, it is 60 over here, and 19 over here. So it is a much better figure of merit. See here, it is much lower. Okay, this is low. This is also not pretty bad power. This has very good power, very low power, and even then you come up with a speed which is quite pretty decent. And see here again, so they keep playing with different parameters. You have some series which can operate at a higher speed but also low power, and those combinations have been tried out exploiting the technology. You can see even the maximum clock rate which is available is different. So this can work up to even 200, because this is slow. Directly comes from your propagation delay. Okay, it is twice, almost twice. So you see half, almost half. Fan out, how many devices you can connect on the output of, or how many more gates can be derived or can be connected on the output of a particular series. See, to begin with, it was only just 10 max. And even this is on higher note. Some of the gates had a fan out of only 5 or 6 or 8. Okay. See, it has increased, and this series have a fan out of almost 40, which is pretty high, pretty high. The CMOS typically offers a very high fan out, and we will see the comparison later. So you can even see the 4 voltages. These 4 voltages are known as the critical voltages, okay, which determine your noise margin. Okay, so you can see even there are variations. This was the typical which we had talked about, 2.4 and zero point 0.4 on the output side, and on input side acceptable values 2 and zero point 0.8, which gave the noise margin of 0.4. But if you see over here, the noise margin for high is 0.7, for low it is 0.3. So it is asymmetric. If you come over here, the high is 0.5 and low is 0.3. Again, it is asymmetric. Okay, but you have some increased noise margin on higher side in this series. So you always need to check on these values, and not only the voltage parameters, you also need to check on current parameters to see if you are trying to use different ICs with different families. Then you have to make a compatibility check as well. This I am again pointing out. Fan out refers to the load drive capability of an IC output. So if a TTL output has a limit on how much current it can sink in a low state or source in a high state, you cannot connect more devices on the output of that node. So if you try to exceed the current, which can be, for example, it is driving a low state, and you connect many devices which are trying to or wanting to sync a higher than this capability, what will it result? It will not be able to sync all the current, and the voltage level will not be the desired value. So you get a undesired value of output. You can determine the fan out and fan in capability for any mixing as well. So you can add all the IIH requirement of all the devices which are being driven by a node, by an output node, and that sum should be less than the IUH specification of the gate who is driving. So we will try to see this example in interfacing and complete. Same is for logic low. You need to check what is the total sum of current required, and that's how. See, this is what it means. This is the output node. So this node can sink a particular current. This now device is connected to, let's say, two gate inputs. So they will have some current which need to be synced. So they have a IIL and this has IOL. So the sum of these two IIL should be less than this IOL. Similarly, when you are driving high, the current which is this is sourcing should be higher than the sum of these two currents required. Okay, only then your circuits will work, else they will not work. So it's very important because we are the electronic system designers. We want to be and aspire to be that. So hardware also is important on which we are building our softwares. But the when you are doing a hardware design, corresponding hardware design, you need to take into account all those things. Now, though we do talk about only digital, we are interested in zeros and ones, but what lies behind 0 and 1 is important, and therefore interfacing is very, very important. Now, if you have a unconnected or floating input on a TTL IC, then what do? All the inputs are 1 if they are not connected to some logic signal. So if an input is left unconnected, it is said to be floating, but better is you don't leave them floating. See, this unconnected is typically floating. So it is treated as logic 1. It is better is you connect it to a logic 1 through a resistance, or whatever way you are connecting, or logic 1, the way you are applying logic over here, you apply logic 1 over here. Or if one of the input, or you can do second thing is you short this with another input. So whatever comes here, it goes there also, and the logically the function does not change. It becomes a, rather than a 3 input device, it becomes a 2 input device. Okay, so this can be done. So you have two options, either connect it to logic 1 or short it. Though it says there is an option that you can leave it unconnected. Okay, but the suggestion typically would be don't leave any node floating. The thing is, this is also important when you are connecting two nodes to the same input. So the load will definitely increase. What we did here, see here. Now this node will be driven by another gate. For example, this gate is driving it. So rather than driving just this one gate, it has to drive two gate. So this load will slightly increase. Okay, so I'll uh, okay, if you for example, a clock which is normally low and you want to activate only on some time, then you can put it through a switch which turns it on and off, and you can put that way. These also can be designed as a hardware circuit, the clock generator, etc. We are not worried much about this at this point in time. Okay, so I'm not much bothered about it. Not this even. I am more interested into the hardware interfacing. Okay, so I think today, oh, sorry, I have already run out of time. So I am stopping over here. Only one thing or two things are left. One thing is I wanted to do TTL to CMOS and CMOS to TTL interfacing, which needs something like 20 to 30 minutes, taking few examples for you. And I wanted to do you the hazards, which are very important from placement point of view. Maybe we don't even ask a question in the exam. That is not an issue, but you should know it to prepare for your interviews. So I will kind of like to take next class on Monday, the same time, 10:30, though formally lectures are over, but treat this as an extra class, and I'll take on Monday, 10:30 to brush you up on interfacing, which is very important. Of course, this is mandatory. Everyone should know it. And something on static or dynamic hazards. Okay. Any question on this? I'm sorry I had to rush through because of the classes which got reduced and I couldn't do in detail. But if you wish that I should do the operation of these TTL gates in detailing, I'll do it. I can do it. You can let me know and I can engage an extra class and can do it for you if you wish. CRs can kind of find out, and those who are interested can tell me. I can even engage class for 10 students if they are interested. I have no issues. Is that okay? Yes, please.
Yes, ma'am.
ठीक है प्रणव. So,
Yes, ma'am.
Pranav, you can kind of find out if anybody or one-to-one, if you have problems and you want to talk to me one-to-one, you can send a message on WhatsApp even, that is more convenient, and I can engage the sessions with you. I can
Okay, ma'am.
club together and I can engage sessions on the similar problems.
Yes, ma'am.
Okay. And I just saw, I'm seeing baby Shabnaz. Baby Shabnaz,
Yes, ma'am.
why are you connected over here? You are a
Sorry,
MTech.
ma'am.
You are a
Actually,
MTech student. You have connected
yes,
wrong
ma'am.
class.
Okay, ma'am. Sorry.
Okay. Okay. So all the best. Today you have a quiz. I know. All the best to you for the quiz. And yeah, I'm sure you have checked all the details on the LMS. I had not been involved in that. I couldn't. So please check out and let me know. Okay. All the best to all of you. Yes, anyone else who wants to say anything or any issue? Else, Pranav, will you, who was,
Yes, ma'am.
you will convey to the class now? We are having meeting at 10:30 on Monday.
Okay, ma'am.
हाँ, अगर उस समय शेड्यूल में कुछ और हो तो मुझे बता देना एंड व्हाट इज द कन्वीनियंट टाइम मुझे बता देना, मैं उस समय लगा लूंगी.
Okay,
But
ma'am.
else, let's fix at 10:30 on Monday so that we wind up quickly. ठीक है?
Okay, ma'am.
Okay, all the best.
Thanks.